Okay, so for today, I will discuss on the lateral earth pressure, okay, uh, which is related to the dynamic load. Okay, then after that, we may learn on the brace cut design. Okay, so all related to the lateral earth pressure. However, for the brace cut, okay, it is based on the static condition. Okay. So for tomorrow morning, okay, we will start at 9. Okay, so I will teach on the Euro Code 7, okay, under the geotechnic uh, design, geotechnical design. Okay, we may learn on the shallow foundations and also deep foundations. Okay, so for tomorrow, we will try to end before 1 o'clock. Okay. So then later on, I will upload for any assignment, okay, on the e-learning. Okay, most probably on the Monday or Tuesday. Okay. So for today discussions, okay, we will discuss on lateral earth pressure on retaining walls. Okay. So basically, it is similar from what we learned on the Rankine or column approach, okay, where we use the static approach, okay, and then there will be some modification has been made by several researcher, okay, or a scholar, okay, to be used related to the earthquake event. Okay. So the increase of lateral earth pressure during earthquake induce sliding or tilting to the retaining structure. The majority of case histories of failure reported in the literature until now concern on waterfront structure, such as quay wall and bridge abutment. So some of the example of failure and lateral movement of quay wall due to earthquake are given in table 1. Okay. So I have listed all the event, okay, which is has been recorded since 1930. Okay. And most of the event, okay, due to the earthquake, okay, are located at Japan. Okay. Only one held in Chile. Okay, while the rest is happen in Japan. Okay, so this is the quay wall, okay, which is to allow for the ship, okay, to load or unload their loading, okay, and get nearby to the harbor. Okay. Okay, Sid and Whitman have suggested that some of these failure may have been due to several reasons, okay, such as increase of lateral earth pressure behind the wall, reduction of water pressure at the front of the wall, and the last one is related to the earthquake, which is liquefaction of the backfill material. Okay, then a comprehensive review on the dynamic lateral earth pressure studies conclude that the theory can be divided into 3 broad categories. Okay. The first one is based on the fully plastic or static solutions, solution based on elastic wave theory, and the last one is solution based on elastoplastic and non-linear theory. Okay. However, the author has mentioned here, okay, because of the complex soil structure interaction, okay, mode of wall movement during earthquake, the lateral earth pressure theory based on the fully plastic solutions, which is widely used by most of the design engineer, is detailed in this chapter. Okay. So for this discussion, okay, we use the improvised solution from the fully plastic solutions. Okay. So in earthquake engineering, to analyze the seismic response of soil embankment and slopes, simply adding a permanent body force representing the earthquake shaking to a static limit equilibrium analysis. Yeah. So this is approach has been made to include the seismic response, okay, by adding this response on the static limit equilibrium. Okay. So before we discuss on the lateral earth pressure due to the dynamic, okay, so we should have revised, well, we look again on the static loading. Okay. So analysis and determination of lateral earth pressure are necessary to design retaining wall or retaining structure. Okay. As we know, there are three categories of earth pressure. The first one is earth pressure at rest. Okay, where there are no movement happen. Okay, so means that the conditions is in a stable. Okay, where they call as an elastic equilibrium with no lateral strain taking place. Okay, then the second one is the active earth pressure plastic equilibrium with lateral expansion taking place. Okay, so this is where there are movement and the soil reach the failure state. Okay, then there will be a passive earth pressure. Okay, where the plastic equilibrium with lateral compression taking place. Okay, so the active is on the expansion while the passive is on the compression. Okay, so this is the illustration diagram to show the how does the conditions of the soil after has been experienced lateral load at rest, lateral load in active, and lateral load in passive. Okay, so this is the compression of this is expansion. Then while this is the compression. Okay, so for the at rest, okay, we may calculate for the effective stress, effective vertical stress, and then we may multiply with the K naught in order to get the value for the lateral earth pressure. Okay. So that is the formula there for the K naught is equal 1 minus sine C. Okay. So there are no value of the C, okay, due to the condition has not reached the failure state. Okay, so there are no C value to be used. Okay, so for the active and passive, we have here a Rankine. We may use the Rankine theory and also the column theory. Okay. We may use the Rankine theory and the column theory. Okay. However, uh, for for the dynamic approach, okay. So the scholar has improvised the column theory instead of the Rankine theory. Okay. So for the Rankine column theory, okay, the assumption has been made here, okay, no addition of friction between wall and soil, and it is assumed that the wall is smooth, okay, for the Rankine, okay. And for the column, there is a friction occur between wall and soil, okay. And both of the Rankine and column assume that failure occur in the form of wedge, okay. So this is also applied to the Rankine, where they assume that failure occur in the form of the wedge. Okay. So failure is assumed to occur in the form of the sliding wedge along the failure plane. Okay. So the direction of the resultant pressure is parallel to the backfill and act to 1/3 from the wall base. Okay, could be used for cohesiveness and cohesion material. Okay, so this is a condition where an active lateral load happen. Okay, while this is the passive lateral load conditions. Okay. So the 1/3 actually is based on a single layer of soil. Okay. So for example here, okay. So if we draw the distribution diagram, okay, for a single layer of soil, okay. So we will have this kind of diagram. Okay. So this will be the H, and to obtain the what we call as the effective vertical stress, okay. So the unit weight of the soil should be multiplied with the height. Sorry. The unit weight of the soil should be multiplied with the height, and then we should apply the KA or KP. Okay. Okay. So that will be the pressure acting at the base of the what we call of the retaining structure, for example. Okay. So in order to obtain what will be the load, okay, so we need to get the area of this triangle. Okay. So 1 or half, okay, times unit weight times H power by 2, and then time KA or KP. Okay. So that is for the we call as a PA, active load. Okay. So based on the concept of moment, okay, to identify where is the location of this load, okay. So by assuming the this is the point, okay, or the datum that we may use, okay. So for the moment arm for a triangle, okay, based on the this if this is the point or base point, okay. So then it is considered as the 1/3 or 1/3, okay, based on the from the base. Okay. So this PA acting at 1/3, okay, from the base, okay, for a single type of soil. Okay. So for example, if it is a multi-layer of soil, okay, so we could not directly use this equation, okay. So we need to draw, or we need to determine the distribution diagrams. Okay. So from there we need to get the area. Okay. From the area we may need to determine the moment. Okay. In order to get the line of action. Okay. So this is only for a single layer of soil. Okay. However, then for our discussion, we rely on single layer of soil only. Okay. Okay. In 1976, okay, Column derived an equation for active earth pressure on a retaining wall due to a dry cohesiveness backfill. Okay. Okay. So this is the formula that we have discussed. Okay, based on single layer of soil. So the Ka we may determine by using this formula. Okay. So we need to know what is the meaning of each notation. Okay, for here the phi is the soil friction angle, beta is the slope of the back of the wall with respect to the vertical. Okay, so this is the beta. Okay. So then we have here delta. Okay. Angle of friction between wall and the soil. Okay. So this is the friction between wall and soil. Okay. So normally this value, okay, first it should less than the phi. Okay. It should not greater than phi value. Okay. Secondly, okay, if we are not being provided with the value of this data, so we may assume it is 2/3 of the fee. Okay, so that is for the friction angle between wall and soil. Okay, then we have here I. Okay, I is the slope of the backfill with respect to the horizontal. Okay, so if the condition of the soil at the back of the retaining wall is flat, okay, so it means that the I value is equal to 0. Okay. So for example, if the retaining wall has been constructed in the straight condition, okay, so means that the beta is equal to 0 as well. Okay. Okay. Uh, this equation, okay, the Ka, okay, also could be determined by using what we call a chart, okay, a table, okay. So okay, this is the table to determine the Ka, okay, without using the equation, or actually this table has been derived, has been calculated based on the equation, okay. So in the actual design of retaining wall, the value of the wall friction is assumed to be half phi and 2/3 of phi value. Okay. So the active earth pressure coefficient for various of phi, I, and beta with delta range from 0 to 25 and 2/3 of phi are given in table 8.2 and 8.3. Okay. So for this table 8.2, okay, the beta value is equal to 0 and also I is equal to 0. Okay, similar to what I have discussed here. Okay, so means that the retaining wall has been constructed in a straight cut. Okay, and also the backfill is in a flat shape. Okay. So then by knowing what is the value of the fee, okay, and also the value of the delta, so we can get the value for the KE. Okay. So there will be another table which is on 8.3. Okay. So from this table, by knowing the value of the delta is 2/3 of the fee, okay, so then we can determine the KA value, okay, with a different, various value of I, okay, which is the slope, which is the gradient of the backfill, okay, phi value, and also the beta. Okay. So from there we can get the value of the Ka. Okay. So for example, by using the 8.2, okay, the delta value is range the delta value is 17. Okay. So we may use the interpolation approach. Okay, for example, 0.3251 equal to 15. Okay. And then we want to find what will be the 17, which is the x. So then for the 20 is equal to 0.3203. Okay. So we use the interpolation approach to get the value exactly for the 17 degree. Okay. So if it is very time consuming, so we'll be back to the whole equations for the Ka. Okay. Okay, so that is for the static approach. Okay. So then we may look on the dynamic load. Okay. So there are some improvement has been made, okay, by several researchers. Okay. For example, here Mononovi or Carbi, okay, and then we may have another scholar. Okay, if I'm not mistaken, his name is Arango. Okay, where he also has improvised the Mononovi or Carbi approach. Okay. So column active earth pressure equation, it can be modified to take into account the vertical and horizontal coefficients of acceleration induced by the earthquake. Okay. So in here we have the KV and KH due to the earthquake. Okay. So this is generally referred to as the Mononovi or Carbi analysis. Okay. Which has been proposed in 1929, okay, by, it's actually from Okabe in 1926, and then it's been improved by Mononovi in 1929. Okay. So the Mononovi Okabe solution is based on the following assumption. Okay. So the failure in soil takes place along the plane, such as BC shown in figure 8.2, okay, which is similar with the column and Rankine approach. Okay. So this is the condition of the failure. Okay. However, there are additional notation here, okay, where they include the KV and also the KH. So there will be a slightly changes of the force polygon from the static approach by adding the KH and also the KV. Okay. So the movement of the wall is sufficient to produce minimum active pressure. Okay. So the shear strength of the dry cohesiveness soil can be given by the equation of S equal to sigma prime tangent phi, okay, where the sigma prime is the effective stress and S is the shear strength. Okay. So at failure, full shear strength along the failure plane, okay, BC is mobilized. Okay. The soil behind the retaining wall behaves as a rigid body. Okay. So figure 8.2 show the force considered in the Mononovi or Carbi solution. Okay. Line AB is the back face of the retaining wall, and ABC is the soil which will fill, is similar with the Rankine and column. Okay. The force on the failure wedge per unit length of the wall are the width of the wedge W, okay, acting force PAE, okay, and then the resultant of shear and normal force along the failure plane F, and the last one is the KHW and KVW, which is the initial force in the horizontal and vertical direction respectively. Okay. So that is for the KH and KV. And the G is the acceleration due to gravity. So they include the KH and KV, okay, in the normal static approach, okay, to be used for the dynamic loading. Okay. Okay. So the active force determined by the wedge analysis described here may be expressed as, okay. So previously we doesn't have this one. Okay. And to differentiate between the static and the earthquake, so this Mononovi or Carbi approach has included the E. Okay, so in here means that we determine the earthquake condition, where we include the PAE and also the KAE. Okay, so then they have improved, okay, the active static pressure coefficient, okay, which is the KA, So they define as the KAE. Okay. So the difference is adding the theta in the formula. I guess the rest is similar. Okay. So what is the formula for the theta? Okay, tangent KH over 1 minus KV. Okay, so that is for the theta. Okay. So for the active force condition, PE, the angle alpha that the solid which ABC located behind the retaining wall, okay, mixed with the horizontal KV, which is equal to 0, beta is equal to 0, I equal to 0, and phi is equal to 30, and delta is equal, so sigma is equal to 0 to 20, is shown in figure 8.3. Okay. So 8.3 is to identify what will be the alpha value, okay, which is here. Okay. So what is the degree of the wedge failure? Okay. So we can determine the alpha value, okay, but it's not very important to be used in the calculation. Okay, then implications. Okay, okay, this one. So for example, first if the phi minus theta minus I is less than 0, so it will become negative. Okay? So no real solution of KEE is possible. Okay. So then physically, it implies that an equilibrium condition will not exist. Here, for the stability, the limiting slope of the backfill may be given by I should less than the phi. Okay, so it means that the degree of the slope of the backfill should not greater than the phi value. Okay, so in order to ensure that the value of this part should not be a negative, okay, so we need to control the I. Okay, because we could not control the theta because the theta is due to the earthquake event. Okay, and we can little bit control on the phi, okay, by make sure that the compaction is very good enough. Okay, so for no earthquake condition, this is theta equal to 0. For stability, give the familiarization where the I should less than the phi minus theta. Okay. Secondly, for horizontal backfill, I is equal to 0. For stability, the theta should less than phi. Okay. So that's why the compaction effort is very important to reduce, okay, of the failure due to the earthquake event. Okay. So by increasing the effort of the compaction, okay, we also can increase the phi value. Okay. So since theta is equal to the tangent KH over 1 minus KV, okay, for stability, combining result in KH of KH less than 1 minus KV tangent phi, okay, here's the critical value of the horizontal acceleration can be defined. Okay. So this is just to ensure that, okay, or to determine what will be the critical KH value, okay, related to the KV. Okay. Okay, then later on, okay, an approach has been made, okay, by Arango, okay, by improvise the Mononovi or Carbi, okay. So yeah, means that for the Mononovi or Carbi, by using this formula, okay, so we can get the value for the lateral stress, okay, the active lateral stress due to the earthquake. Okay. So another approach being made by Arango, okay, develop a simple procedure for obtaining the value of KAE from the standard chart of KA. Okay. So this is the static approach, okay, where they have a PA equal to half gamma H square KA. Okay. So then they come up with this what we call this equation. Okay. So then for the dynamic, okay, so this is the KAE, okay, and then they come out the same approach, okay, with the static to have this kind of equation. Okay. So for the AC is equal to KA cos square beta, okay, while for the AM is equal to KAE cos theta cos square beta. Okay. So then for the AM, okay, so the Arango has proposed the use of the I prime and also the beta prime, okay, to make sure that the equation of the AM and AC have the same number of notation. Okay. For example, here phi minus beta, and for this dynamic, phi minus beta minus theta. Okay. So by introducing beta prime, beta plus theta, so slightly it show the same notation with the static one. Okay. So the difference is only beta prime for the dynamic. Okay. So this will be beta prime for the dynamic, I prime for the dynamic, I prime for the dynamic, beta prime for the dynamic. Okay. Okay. So the preceding equation is similar to equation 8.13, except for the fact that I prime and B prime are used in place of the I and beta. In those, it can be said that AM equal to AC I prime beta prime, okay, which is equal to KA I prime beta prime cos square beta prime. Okay. So the active earth pressure PAE now can be expressed as PAE half, okay, so H square minus times 1 minus KV, okay, cos square beta prime cos theta cos square beta KA times I prime beta prime. Okay. And then they simplify to this equation, okay, which PA I prime B beta prime, okay, times I minus KV, and introduce the P asterisk, which is this equation. Okay. So the P asterisk is the cos square beta prime minus cos theta cos square beta. Okay. So this is the procedure. Okay. So the one that we have discussed here is how they come up with the improvise of the Mononovi or Carbi equation and relate with the static approach. Okay. So now we look on the procedure. Okay, how could we use this Arango approach, okay, to determine the PAE? Okay. So for the first one, we should calculate for the I prime. Okay. And before that, we should determine the theta. Okay. So the theta still we use this formula. Okay. So this is the formula of the theta. So in order to get the I prime, so we need to know the theta as well. Okay. Then calculate the beta prime, okay, with no value of phi, theta, I prime, and beta prime. Okay, so we may calculate of the KE from table 8.2, 8.3 or other available chart. Okay, so means that we still can use the static table from table 8.2, 8.3. Okay, so by assuming I prime is equal than I, okay, and also beta prime is equal than beta, so we can use the static KA to represent for the KAE. Okay, so then calculate PA is equal to half gamma H square KA. Then calculate for the 1 minus KV. Okay. Then for the asterisk P, okay, so asterisk P can be obtained from this formula. Okay. So then calculate for the PAE is equal to PA times I prime beta prime times 1 minus KV times P asterisk. Okay. So the P asterisk also can be determined based on this figure 8.5. Okay. So you know what we need to know what is the theta, okay, and then relate with the beta value. Later on, determine the asterisk P. Okay. So that is the procedure by using this Arango approach. Okay. Okay. So this an example, okay, by using the Arango approach. Okay. So we have here beta is equal to 0, I is equal to 0, phi is equal to 36, okay, sigma is equal to 8, delta is equal to 18, H is equal to 4.5, and then we have here gamma 17.6, while KV and KH is equal to 0.2 and 0.3 respectively. Determine the active force per unit length of the wall. Okay. So the first procedure, determine the theta. Okay. So in this case, the value is 20.56. Okay. Then obtain the I prime, okay, which is the I prime is equal to I plus theta. Due to the theta is equal to I equal to 0. So I prime is equal to theta. And also due to the beta is equal to 0, beta prime is also equal to theta. Okay. So then, okay, we may determine the Ka, okay, by using the same equation of the static. Okay. So then we can calculate for the Ke. Okay. So the value of the Ka is equal to 0.583. Okay. For example, if we want to use the table, okay, so we need to look on table 8.2 or 8.3. Okay. So in this case, the beta is equal to 0, I is equal to 0. Okay. So I guess we look on the table, what we call table 8.2. Okay. Because the delta, okay, I guess is not equal to the 2/3 of the phi. Okay. So for example, what will be the 2/3? Okay, by having 36, okay, 36 times 2 over 3, okay, the delta should equal to 24 in order to use the table 8.3. Okay. So then the phi is equal to 36. Okay. So we look on the table 8.2, for example. Okay. Can we use this table or not? Okay, to get directly the Ka value. Okay. So we have here 36 for the phi. Okay. However, for the delta here is equal to 18. Okay? So it's very difficult to get the exact value for the Ka when the delta is equal to 18. Okay? So if we are using this interpolation, okay, and then it's very time consuming, so it's better for us to use the equations of the Ka directly. Okay? So the Ka is equal to 0.583. Okay. Then the PA, okay, can be determined as half times gamma times H square times Ka. So this is the PA value, okay? But still it is not a actual PA because we use the I beta and I prime and beta prime. Okay? So if you want to get and compare what will be the difference between the static and the earthquake, okay? So you need to not include the KV and KH. Okay, means that the theta should not be included. Okay. Okay. So then this is the value of the PA. Okay. So we need to count for the PS3. Okay. Because the final equation, okay, is similar with this one. Okay. So then get the PS3 0.9363, or we can use the this chart, okay, to get the PS3. Okay. With the theta is equal to, what is the theta value here? Theta is equal to, theta 20.56, okay? And the beta is equal to 0, okay? So almost here. So then the value for the asterisk P, okay, is around 0.9363, okay? So in here we obtain 0.94 something, okay? Okay, so that is for the asterisk P. Then for the 1 minus KV is 1 minus 0.2. So the final value for this lateral earth pressure due to the earthquake is equal to 77.81. Okay. So this is the solution for these problems. Okay. Okay. So the effect of the various parameter on the value of the active earth pressure coefficient. Okay. So parameters such as the angle. So then the author look on the influence of different parameter. Okay, that on the earth active earth pressure due to the active pressure of the earthquake. Okay, coefficient. Okay, so they look first on the angle of the wall, the friction angle of the wall, and then friction of the soil, and also the slope on the backfill of the backfill, which is the I. Okay. So the first one, the effect of the wall angle, the effect of the wall friction angle on the active earth pressure coefficient is rather small. Okay. So although the KH is increased, okay, so there are no significant difference of the KAE on the wall friction angle. Okay. So, however, for the soil friction angle, which is the phi, okay, so here they come up with the conclusion that, okay, the KAE, okay, when the value of the phi is equal to 30, is about 35% higher than the KAE when the phi is equal to 40. Hence, a small error in the assumption of the soil friction angle could lead to a large error in the estimation of the PAE. Okay? So please make sure that we get the right value, okay, on the phi, okay, which is obtained from the undisturbed sample from the laboratory test, okay, in order to reduce the effect of the soil friction angle. Okay. So the last one is the effect of the slope of the backfill. Okay. So from here, okay, we notice that the value of KAE cos delta sharply increase with the increase of the slope of the backfill. Okay. So when the KH is increased, okay, so the KAE cos delta will sharply increase. Okay. So it means that uh, 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 there will be a significant effect on the slope, on the soil friction angle, and also on the slope of the backfill. Okay. And there will be no significant effect due to the wall friction angle of the soil and also of the retaining wall. Okay. So there is finding that is conclude based on different or based on various parameter. Okay. Okay. So this is the last subtopic, okay, for the lateral earth pressure. Okay, by using a graphical construction, okay, for determination of the active force PAE. Okay, actually, it is based on the Coleman. Okay, Coleman in 1975 developed a graphical method for determination of the active force PA, okay, developed behind a retaining wall. Okay, so this PA can be determined by using a graphical methods. Okay, so in order to use this approach, okay, we need to draw the problems on graph paper. Okay, so we need to use a graph paper or grid paper to draw the problems, and then from there we can determine the exact value for the PA or PAE. Okay. So a modified form of Coleman graphical construction for determination of the active force PAE per unit length of a retaining wall has been proposed by Capilla in 1962. Okay, so then Capilla has improved the Coleman approach, okay, to include the dynamic load or the earthquake event on the Coleman approach. Okay, so in order to understand this, okay, consider the force polygon for the wedge ABC, okay, as shown in figure 8.2. Okay, so actually the same with the one that I've discussed in the Mononovi or Carbi. Okay. For convenience, this has been replotted in figure 8.9a. Okay, so where they come up with the degree value for the theta, okay, and also for the alpha minus phi in the polygon diagram, okay, which is illustrated in figure 8.9a. Okay. Sorry. Okay. So the force polygon can be reduced to a force triangle, okay, with force PAE Fn a W square root minus 1 minus KB square and KE square. okay, which is in figure 8.9. Okay. So then they have simplified the 8.9A polygon to become to 8.9B diagrams. Okay. Okay. Note that in figure 8.9A, B and alpha is the angle that the failure wedge meet with the horizontal, okay, which is the alpha that we have discussed previously. Okay, which the alpha, where the alpha, okay, is the angle or the gradient, okay, of the wedge failure with the horizontal line. Okay. So the idea behind the graphical construction is to determine the maximum value of PAE by considering several trial wedge. Okay. With reference to figure 8.9c, following a step for the graphical constructions. Okay. So, okay, then, okay, this is the modified Pullman construction, okay, where we need to draw the problems on the graph paper because we need to use the actual scale, or we need either we rescale it again, okay, to get the value of the force, sorry, of the loads. Okay. So this is the list of the procedure, okay, that you may use, okay, to determine the value for the PAE. Okay. However, for this note, okay, I did not provide the example for the what we call it for the static approach. Okay, however, I include for the dynamic load. However, I include an example based on the static Coleman approach. Okay. Okay, so now we look on the procedure. Okay, how could we obtain the PAE, okay, from this Coleman graphical diagrams? Okay. So first we need to construct, okay, the actual problems in a graph paper or in a grid line paper. Okay. So this is the retaining structure, okay, and then it has a beta of certain value. Okay. So then this is the backfill. Okay, this is the backfill. Okay. And we should know what is the I value, or the I value will be provided. Okay. So the same procedure with the Coleman. Okay. However, when we use when we include the earthquake condition, so we may introduce the theta. Okay. Okay. So for the first step, okay, based on the procedure here, okay, draw line BE which make an angle phi minus theta with horizontal. Okay. So phi minus theta, okay, means that we need to count. Oh, sorry. So we need to count. Oh, sorry. We need to get the theta value, okay, based on the formula that we have discussed here before. Okay, the tangent KH minus over 1 minus KV. Okay. So that is for the theta. Okay. So phi minus theta, okay, we get the value. So we need to use the protector. Okay. and draw the line of BE. Okay, so this will be the first step on the graph paper. Okay, so actually the theta is the first step, okay, to get the value of the theta. Okay. So draw a line BD which make an angle 90 degree minus theta minus theta minus delta minus theta with the line BE. Okay. So get the value for this value first. Okay. This equation, and then based on the BE line, okay, we need to construct for the BD line. Okay. So that is for the second step. Okay. Draw BC1, BC2, BC3, which are the trial failure surface. Okay. So the next step is to construct for is to get the value of the trial which failure. Okay. So for example, okay, we may have a same distance, okay, or we can use a constant value. For example, uh, okay, for example, if you want to use 2 centimeter, 2 centimeter, 2 centimeter, 2 centimeter, okay. So then the distance between A to C1 is 2 centimeter, C1 to C2 2 centimeter, C2 to C3 2 centimeter, C3 to C4 2 centimeter, for example. Okay. So then we construct a line from B to C1, B to C2, B to C3, and B to C4. Okay. So what is the function of this line? Later on, we need to determine the area, okay, to get the value for the width, the width of the width. Okay. So that will be the third step. Okay. So determine the KH and KV, and then this will be provided KH KV, okay, and then uh, square root of 1 minus KV square plus KH square. Okay. Okay, so this is not related to the diagram, okay, but we should count this value, okay. Why? Later on we may use it to multiply to get the W value, W prime value. Okay. Sorry. Okay. So then determine the width W1, W2, W3, okay, respectively per unit length at the right angle to the cross section shown. Okay. So the W1, okay, is the area of ABC, then times with the unit width. Okay. So there from there we can get the W1, W2 as well, and to W4. Okay. So we have here W1, here W2, W3, and W4. Okay. So from there we may multiply the W1 with the square root of 1 minus kV square plus KV square, okay, to get the W prime. Okay. So the seventh step is to adopt a load scale. Okay. So what does it mean? Okay. Once we identify what is the W1, okay. So for example, we identify that the value is around 2000 kilonewton. Okay. So then we come up with a scale, okay, where 1 centimeter is equal to 2000 kilonewton. Okay. So that will be the scale that we may use to solve, to get the value of the PAE later on. Okay. Okay. So using the log scale adopted in step 7, okay, draw BF1, which is equal to W1 prime, BF2, okay, W square prime, BF3, W equal to W3 prime on the line BE. Okay. So the okay, 1, 2, 3. Okay, the fourth step on this diagram. Okay. So once we know what is the W prime value, okay. Okay. So then by using the same scale, okay, that we have proposed, okay. So draw a line, for example, B to F1, which is represent the W1 prime value, okay, and F1 to F2 represent the W2 prime, okay, and F3 prime, which represent the F2 to F3, okay, and W4 prime, which is represent from the F3 to F4. Okay. So that is for the step number 4 in the diagram. Okay. Okay. So 7, 8. Okay. Then draw F1G1, F2G2, F3G3 parallel to the line BD. You note that BF1G1 is the fourth triangle to the trial which ABC1 smaller to that shown in figure 8.9b. Okay, similar. Okay, okay. Then the next step, okay. Okay. So the next step is to draw this G1, G2, G3, and G4. Okay, so how to draw this diagram? Okay, so we may use the BD line, okay, as the guidance. Okay, so from the BD line, okay, so we need to draw a line which is from the F1 to the line of the BC1 until it meet the line of the BC1, and it should parallel with the line of the BD. Okay, so how to show the sign of parallel? Okay, okay, so it should be parallel. Okay, so we need to use a ruler here. Okay, or whatever. I guess a ruler. Okay, to make sure that it is parallel. Okay, so F1 will be extend. The point of the F1 should be extend to the line of the BC to get the G1. Okay, Same go to the F2, should be extend to get until it reach the BC2. So that is will be the G2. Okay. So the third one is the F3. Okay, should be extend until it reach meet the BC3. So that is will be the G3. And the last one is the F4 should be reach to the BC4. So it is the G4. Okay. So that will be the step number 5 in the diagram. Okay. So the sixth step is to join the point G1, G2, and G3. Okay. So then you need to use what we call as elastic ruler, okay, to combine the line, to combine the point of G1, G2, G3, and G4. Okay. So that will be the step number 6. Okay. In the diagram. Okay. So you need to use the elastic ruler. So draw the line, okay, to join all the G1, G2, and G4. Okay. So draw a line HG parallel to the BE. Okay. Let G be the point of tangency. Okay. So then, okay, you need to draw a line of HG. Okay. Where it should also tangent with the what we call with the curve from the step number 6. Okay. And it also should parallel with the BE. Okay. So that is for the step number 7. Okay. So okay, then draw line GF parallel to BD. Okay. So the last is, once we identify, okay, the tangent point, okay, so from here we need to draw a line until it meet the BE and also parallel with the BD. Okay, so that will be the F value. Okay, so this F value, okay, actually is the force of PAE. Okay, so then I guess we already so then get the distance from B to F and then apply with the scale to get the value of the PAE. Okay, so the F is the value of the PAE, but we need to get the distance of the BF, then multiply with the scale. Okay. So that is the procedure. Okay. So it up to 8 steps to solve or to get the value for the PAE.
Okay. Sorry, Doctor.
Yes.
For the PAE equals to BF times the load scale or GF line times the load scale?
Sorry. BF?
BF line or GF line, because the notes you written here is GF.
Yeah. Oh, okay. Determine the force as GF time lot scale. Lot scale. Okay. I guess BF, because we have scale all the we draw the BF1, BF2, okay, based on the same scale or from the same W1 prime. Okay. But we may look on the Coulomb example. Okay. Let me show the Coulomb example first. Okay.
Okay.
Okay. Thanks for the question. Okay. Okay. Okay, so that is the procedure for the graphical construction. Okay, we look on the Coleman example. Let me open it first. Stop. Okay. Okay, so this is based on the static Coleman approach. That is parent to AG. Okay, yeah. I guess you are right. Okay, means that the distance between the tangent point to the AC, okay, is the value for the PE. Okay, so not from the A to the point of this the line that we obtain. Okay, because in here, okay, the length of this line applied to the width scale give the value of PE. Okay, a line from point A to the tangent point define the failure plane. Okay, yeah, you are correct. So and actually the slide is also correct. Okay? So means that the GF is the value for the PE. Okay. Okay, so this is example based on the Coleman. I have add on your what we call on your e-learning. So the value of the PE is the length of this line times the scale value. Okay, however, on for the Coleman, it doesn't include the theta. So this is you should include theta based on the capilla approach.
Sorry, doctor, please.
Yes.
This example, yes, this is example. Can we find in e-learning, right?
Sorry.
This is example. Can I find in e-learning, right?
Yeah. I have include
Thank you.
in the e-learning. Okay?
Thank you, doctor.
Okay. So I have complete on the lateral earth pressure. Okay, so we should have a rest for 5 minutes, and then we may continue for the brace cut. Yeah, we'll stop first. Okay, we should start at 3:22. Okay, so you can make a coffee or you can go to the rest room. Okay.